All right, so we'll jump right into lecture 41. Lecture 41 actually covers your solo exercise 6. So if you have done all of those panels and answered your questions, we will go over those in this lecture. All right, so your first panel here, you were provided some initial spin, 37 degrees, and AHG. And if you did your crossing off procedure, you would identify the antibody as Kell. And if you looked at your pattern of reactivity, notice that for every cell on your panel that is positive for Kell, you had a 2+ reaction at the AHG phase of testing. So your pattern of reactivity matches perfectly. And then you're asked some questions about this antibody. It is of IgG classification, hence it is only reacting at AHG. This is considered a clinically significant antibody, meaning that it does have the capability to cause hemolytic disease of the newborn and can cause a transfusion reaction. And in the event your patient had anti-Kell and was transfused with Kell positive donor cells, that would cause an immediate transfusion reaction. It would be a hemolytic transfusion reaction. One of the questions you have, it asks, what is a key feature of this antibody? Remember, the Kell is the most antigenic antibody, second to D, right? So D is our most antigenic, and then Kell is the second most antigenic. And if you think about it, 9% of the population have the Kell antigen. So you will encounter Kell very often in blood bank. Next to D, it is probably the most identified antibody in blood bank. You'll have a lot of Kells. The good news is that only 9% of the population have the antigen, so it's very easy to find antigen-negative blood. And if you look at our panel, you notice that all of the other clinically significant antibodies are crossed off except for Big E. All right, he is only half crossed off. So you're asked, what are some other methods that we could eliminate this antigen? How could we rule it out? And so this question actually in Blackboard has, I will take 2 answers. Definitely you could run select cells. So you could test with additional panel cells from a different panel. You could definitely run a Kell negative cell, a Big E positive cell. And if you had a negative reaction in your patient plasma, that would rule out Big E. If you phenotyped your patient cells and your patient was determined to be E positive, then therefore he could not build anti-E. So by phenotyping your patient, and if he's positive, you could therefore rule out Big E that way. So if you answered phenotype the patient or select cells, you will get credit for that question. Keep in mind though, phenotyping your patient, if your patient has been transfused within the past 3 months, you cannot adequately phenotype your patient. Okay, and the only reason for that is because they have been recently transfused. Those donor cells could potentially still be in their circulation, and your phenotype result would not be an adequate representation of your patient cells. All right, so anytime your patient has been transfused within the last 3 months, we are unable to do phenotype testing on the patient, all right, with our serological testing. All right, and then the last question, question 10 in your solo exercise, it asks how many units would you cross match to find 3 type specific units. All right, so in this patient case, we are not given his patient type, so we actually don't know what his patient type is, so we can't adequately answer type specific. So we will just honor his Kell. So what % of the population is Kell negative? And again, only 9% of the population have the Kell antigen, so 91% of the population would be Kell negative. So we can divide 0.91 by 3, that gives us 3.3. So we would need to cross-match 4 units. So I don't like the wording of that question because it says type specific, but you have no ABO RH on your patient. So you can't adequately answer type specific. So just honor that Kell for that question. All right, and then panel number 2, you're given some reactions with LIS as your enhancement media, and then you're also given some enzyme reactions as well. So if you take a look at your original reactions, notice that you have one 3+ reaction, and then all of the other cells are 2+. So whenever you see this, a couple of things in your mind. Number one, do you have multiple antibodies present? And that's why screening or panel cell 3 gave you a stronger reaction, or do you have a single antibody exhibiting dosage? All right, so those are some possible scenarios when you have varying strengths of reactions like that. So if you do your rule out procedure, you will see that our 2+ reactions in the AHG phase of reaction matches up with Duffy A perfectly. All right, so every cell that is Duffy A positive, so cells 4, 5, 6, and 7, and 9 gave us a 2+ reaction in AHG. However, we still have this 3+ reaction there on the cell that is Duffy A negative. So that lets us know that there is another antibody in our patient's plasma that is reacting. And if you take a look, this cell also happens to be big E positive, which we had not crossed off yet. So big E is definitely a possibility. All right, and so then you're given some additional information. You have some Physin or enzyme treated cells. So the cells were treated with enzyme. Remember that enzyme will destroy the Duffy antigens from your panel cells as well as the MNNS system as well. So notice after enzyme treatment, and then we run our patient plasma with enzyme treated cells, all of our Duffy reactions have now gone away. And then we are left with 2 cells that have a reaction, panel cell 3 and panel cell 5, which match the pattern of reactivity for big E perfectly. All right, so remember, while Physin destroys your Duffy MNNS system, it also enhances your RH and KID system as well, okay? So that's why we saw this 2+ reaction on panel cell 5 get stronger. All right, it went from a 2+ to a 3+. All right, notice as well, and on the previous panel as well too, Lutheran A is a private antigen, and you'll see this a lot. Notice every panel cell that we have is Lutheran A negative. And so again, he's a private antigen, so most of the population is going to be antigen negative. So we typically do not worry about Lutheran A. And then also Lewis B in this case is not, or Lewis A, sorry, is not ruled out either. So in order to rule out Lewis A, you could probably run some select cells, Duffy A negative, E negative, Lewis A positive, to rule out Lewis A. Question 12 asks, Lewis A is not crossed off, list 2 ways to rule out this antibody. Remember, there's another technique. When we suspect a Lewis antibody, we could do a neutralization. All right, so the neutralization technique, you're treating patient plasma. So you have a, your commercial antisera has the soluble antigen in the antisera. It will absorb out the Lewis antigen from your patient plasma. So you perform the neutralization on your patient plasma, and then you will repeat your panel with that neutralized patient or neutralized plasma. If Lewis was present, then your reactions would become negative, okay? And the most common reason we perform neutralizations is to see if there are any underlying antibodies. All right, so if you have because remember, Lewis is kind of a weird antibody. He's of IgM classification, but he can react at initial spin 37 and sometimes even AHG. So you'll have reactions across the board, and performing that neutralization will get rid of those reactions, and then you're able to identify if there are any underlying alloantibodies as well. Right, and you have one more question in this group that I haven't answered yet. Are there enough positive and negative cells to reach your 95% confidence level in antibody identification? So remember, in order to reach that 95% confidence level, we must have 3 positives and 3 negatives for each antibody that is identified. So we have definitely 3 positives and 3 negatives for our Duffy A. However, for our anti-big E, we only have 2 positive cells, 3 and 5. So if you have a big E positive cell in your IAT, then you could use that cell and that would reach that 95% confidence level. But just based off of this results that we have here, we have not achieved that 95% confidence level for the identification of anti-E yet. Oh, and then the last question asks, what are the key characteristics of your Duffy system? If you guys remember, the Duffy system is associated with malaria. It is thought that the Duffy system offers a receptor site for the malaria organism to bind to, therefore it is able to enter the cell. So those patients that are Duffy A negative, Duffy B negative, which we often see among our African American population, it is thought that with them not having the Duffy antigens present, that malaria cannot bind to and enter the cell. So it is thought to be associated with malaria. Panel number 3, we have some initial spin reactions, we have 37-degree reactions and AHG. Notice that all of our positive reactions are occurring in the AHG phase of testing. Notice that they are all the same reaction strength. So in this event, we suspect one single antibody that is present on all of these cells. Notice you only have 1 negative cell, panel cell number 7 is negative, and notice that your auto control is also negative, all right? So that lets us know that we're not dealing with an autoantibody where you could also see pan reactivity like this, with the exception you would have every cell positive with the warm auto, and we do have an example coming up of a warm auto. All right, so given that we rule out with our negative cells, we only have 1 negative cell that we're able to rule out with. So you do have a lot of clinically significant antibodies that are still remaining. So those that have not been crossed off, you have D, big C, big E, CW, which is sometimes not really included because, again, he is a private antigen. Not a lot of people are going to have antibodies because most people are going to be antigen negative, very rarely. In little s, P1, Lewis A, Chelano, and JKA. If you look at your pattern of reactivity, so everywhere you have a positive reaction in the patient's plasma, how does it match the antigen profile on your cells? And if you look, it matches Chelano perfectly. Notice that the Chelano antigen, it is a public antigen. 99.9% of the population are going to be positive for Chelano. And so every cell except for cell number 7, which matches our patient plasma reactions perfectly. So we can assume that this patient has Chilano, but because Chilano is on every cell, we will still need to rule out all of these other clinically significant antibodies. We'll want to make sure nothing else is underlying, okay? So as the role of the blood banker, that is your role, that's your job, is to make sure you identify every clinically significant antibody, right? And so when you have reactions like this on the majority of your cells, it's going to take some further testing to make sure you rule out all of these clinically significant antibodies. All right, so one of your questions asked, would it be more important to completely rule out Lewis A or Big C? So I hope all of you answered Big C, right? Because Lewis A is considered IgM classification. He cannot cross the placenta. He has not really been documented in any causes of transfusion reactions. So he is really considered more of a nuisance in blood bank rather than clinically significant. However, honoring Big C, it is clinically significant. And so we would definitely want to make sure that we rule out Big C. All right. All right, so what are some ways that we could get rid of these or eliminate our other antibodies? Number one, you could run some select cells, right? This is going to take some work though, because notice you only have one Chilano negative cell on this panel, right? So you're going to have a lot of panel cells in your toolkit. So you would have to have several other panels to choose from. So you would want to choose a Chilano negative cell. You would need a D positive cell, a big C positive cell, big E positive, N positive, little s positive, P1 positive, and JKA positive. All right, so those are all of the select cells. So you would probably run quite a bit of select cells. And there's also another treatment that you could do. You could do a ZZAP treatment, all right? So remember what ZZAP does, it's a combination of enzyme and it will destroy your Kell antigen sites, all right? So you ZZAP treat your cells and then you will rerun the panel. Remember, it's in combination with enzymes, so not only are your Kell antigen sites destroyed, but also your MN and S are destroyed as well. And Duffy's. So by performing the ZZAP, you would really be able to identify any underlying RH antibodies, all right? So we have select cells, we have ZZAP treatment, and then we could also phenotype our patient to see which antibodies they have the capability of building, depending upon which antigens they're negative for. All right, and then moving on to panel 4. If you look at your reactions in panel 4, notice that you have some varying strengths of reactions at initial spin. Also, you have some 1+ reactions at 37. And then you have a negative reactions at AHG phase of testing. So you should ask yourself right off the bat, what does this look like? Do you think it's a cold reacting antibody? Probably not, because you have reactions also at 37 degrees. Is it multiple antibodies? Maybe. You have varying strengths of reactions at 2 different phases of testing. Or is it an antibody that reacts at initial span in 37? So those are some of the questions you have to ask yourself when you see strengths of reaction like this. And if you perform your ruling out procedure, everything is ruled out except for Big C, CW, Lewis B, of course, Lutheran A, and then Duffy B. And if you take a look, so these reactions here, my mind automatically goes to a Lewis. All right, we have reactions at initial spin in 37. I'm automatically thinking this is a Lewis. This is very characteristic of a Lewis to react at initial spin in 37. And if you look at your pattern of reactivity, notice that for every cell that is Lewis B positive, it matches our patient reaction perfectly. So we can assume that this is Lewis B. However, we want to make sure that we rule out Big C and Duffy B. One of your questions asks, what 2 techniques can you use to make this panel negative? All right, so we mentioned that we suspect this to be a Lewis, so this is an instance where we would definitely want to use neutralization. Okay, once we perform neutralization, all of these reactions are going to become negative, and we can make sure there are no underlying antibodies as well. Sometimes with Lewis's, you can also, for this instance, I would be highly suspicious of performing a pre-warm technique because we do have reactions at 37 degrees. Sometimes you will see Lewis only react at initial spin, and in that instance, a pre-warm technique would be warranted as well. So depending on the reactions, you could also perform a pre-warm, but neutralization would definitely make this panel go negative. One of the questions asks, is it necessary to provide antigen negative units for this antibody? There's controversy on that, and depending on what your SOP is, I would say no. Cross-match compatible units in this instance would be sufficient because you have 1+ reactions at 37, negative reactions at AHG phase of testing. So to spend the time antigen typing and reagent use antigen typing is really not clinically necessary. Just to perform an AHG crossmatch and, of course, the initial spin crossmatch would be sufficient. So as long as it's antigen negative, or as long as it's crossmatch compatible, that would be sufficient for transfusion because the Lewis's are not indicated to be associated with hemolytic disease of the newborn or transfusion reactions. Oh, and that last question, what group of patients is the antibody commonly seen? So remember, if you think about your Lewis antigens, remember in order to build an antibody, either Lewis A or Lewis B, you have to be negative for both. You have to be Lewis A negative, Lewis B negative. We will typically see that in the African American population. So it is among those African Americans that we typically see Lewis antibodies, and it is proven that during pregnancies, the Lewis antigen expression decreases when females are pregnant. So we will also see Lewis antibodies during pregnancies for females, just because that Lewis antigen expression decreases. So if you had a clinician, if you identify a anti-Lewis on a pregnant female and a clinician asks you to titer that, remember that it is not clinically significant. It will not cause any harm to the baby because it cannot cross the placenta. There is no need to do any additional testing on that Lewis. Okay, that Lewis is not going to cause hemolytic disease of the newborn. All right, so panel 5, if you take a look at our reactions, we are given some initial reactions using LIS, and then you also have some reactions using PEG. So remember, PEG is a polyethanol glycol reagent. It is used for identification of weak antibodies. So what it does is it removes the water from the testing environment, allowing further uptake of the antibody onto the antigens or onto the cell. All right, so if you suspect that you have a weak reacting antibody, you could try to use PEG to strengthen those reactions. Keeping in mind though, PEG is known to enhance warm autoantibodies. All right, so if your patient has a warm autoantibody, testing with PEG will only make that warm autoantibody stronger. All right, so if you just take a look, just look at your list reactions first, and notice you have some weak plus reactions and you have some 1+ reactions. So we're dealing with some weak reactions, and if you do your crossing off, notice it doesn't really match anything. Your pattern of reactivity doesn't match up. And you will see this in blood bank. This is a real scenario of where your pattern of reactivity doesn't match up with everything. But if you take a look at your little c, right? Notice little c is half crossed off. But if you look at pattern of reactivity, every cell where little c is present, you have a reaction with your LIS testing at AHG, except for pentyl cell 4. Notice pentyl cell 4 is a negative reaction. Keeping in mind, this is one reason why you always have to keep in mind dosage, all right? If you take a look at pentyl cell 4, it's little c positive, but it is also big C positive. So it is heterozygous, meaning that it is sharing the number of antigen sites on the cell with big C. So this cell has big C antigen sites as well as little c antigen sites. So your patient's antibody is already weak, right? It's reacting at 1+, weak plus. All right, so it's already a weak reacting antibody. And if you decrease the number of available antigen sites, the antibody is just unable to bind, right? So that's why we have a negative reaction here. That's why we also did PEG testing as well. And notice when we did our PEG testing that our reactions got stronger, and that pentyl cell number 4 now has a 2+ reaction. If you ask yourself what else you could do other than PEG, you could also do enzyme testing. Remember, enzyme testing will enhance your RHs as well. So I would expect if we were to do a Fison panel on this patient, it would also cause that reaction with pentyl cell 4 to pop out as well. So little c is our most indicated antibody in this scenario. Keeping in mind the reason pentyl cell 4 is negative is because dosage pentyl cell 4 is heterozygous. And then pentyl cell number 6, what every blood bank dreads to see. Notice that you have pan-reactivity. Your panel, every cell is positive. Look at that auto control. It's positive, 3+ at AHG. So this lets us know that he does have a warm reacting autoantibody, okay? Because that auto control is positive, every cell is reactive. So you can't rule anything out. All right, we don't know if there's any underlying allo antibodies. That's the concern with these patients with warm autos, okay? So one of your questions asks, are you likely to find compatible units? Well, keep in mind, everything is reacting, right? Your IAT was positive, your panel is positive, your when you do your DAT, it's going to be positive with polyspecific AHG as well as your monospecific IgG. All right, your complement reaction is variable. Sometimes warm autoantibodies can cause a positive reaction with monospecific C3b, C3d. However, most oftentimes for a warm auto, you probably have a negative C3b, C3d. If you do your eluate, it is going to be pan-reactive. All right, so your eluate is going to react with every cell. Keeping in mind, one way that we can try to get rid of this warm auto is we can try to do a adsorption. We can try to absorb out the warm autoantibody from our patient's plasma. Keeping in mind, If your patient has been transfused within the past 3 months, we cannot use the patient's cells to perform that auto absorption. And the reason for that is if they have been transfused within the past 3 months, they also have some donor cells in their circulation. So the phenotype of your donor cells and your patient cells is going to be different. So if you were to perform a auto absorption and your patient had been transfused within the past 3 months, your donor cells could absorb out the patient's underlying allo antibodies, okay? So that's why if your patient has been transfused within the past 3 months, we must perform a differential absorption. And in Blackboard, if you guys have already logged into your solo exercise, this question had a typo. So it had auto absorption, and it also said acid elution as an option. Okay, that does not make any sense. All right, so the options are now, I corrected it, so if you've already submitted, you'll still get credit. The options are auto absorption versus a differential absorption. All right, so remember, if your patient has been transfused within the past 3 months, you cannot do an auto absorption. We must do a differential absorption, meaning that we use commercially manufactured cells with a known phenotype. You would do 3 separate phenotype cells to try to absorb out that warm auto, okay? I just wanted to make that, clarify that typo in your Blackboard exercise. So back to what I was trying to say, all of your positive reactions on this warm auto, you are not likely to find compatible units for this patient. That is a problem with these patients with warm autos. They're going to react in the cross-match. In your AHG phase of cross-match, you're going to have a 3+ reaction as well. So how BloodBank usually handles that situation, if we have a phenotype established on this patient, we will try to give phenotypically matched least incompatible. So if we can find a unit that has a 1+ reaction rather than a 3+, that's the unit that we want to transfuse, all right? BloodBank will recommend that these patients not be transfused at all, but sometimes the clinicians will decide to transfuse these patients, and in the event they do, they are made aware that this patient has a warm auto, and then we will try to give phenotypically matched least incompatible. However, keep in mind, if your patient has been transfused within the past 3 months, we cannot obtain a phenotype on them. We are unable to phenotype. So unless you already have an established previous phenotype, you would probably just give least incompatible, okay? All right, and then our last panel, panel 7. You have initial spin reactions, 37 and AHG. Notice that we have reactions at 37 and AHG. Keep in mind, so when you see these phases of reactions, you should automatically know which classification of antibody I'm dealing with. Oh, my RH antibodies are known to react at 37 degrees and then get stronger at AHG. Okay, so you should automatically be suspicious of an RH antibody in this scenario. So if you do your crossing out procedure, notice that your pattern of reactivity matches big E perfect, all right? So we have identified big E, and notice also through our crossing off procedure that every other clinically significant antibody is crossed off, all right? So our pattern of reactivity in our antibody is identified as big E, and we've also even have our 95% confidence level. We have 3 positive cells, 3 negative cells. So I want you guys to think about this. Given that we have identified this patient with anti-E, can we infer that this patient has been previously transfused, or if a female has had a previous pregnancy? How did she build this anti-E? she had to have some type of prior exposure, right? This is not a naturally occurring antibody. So if she's a female, she must have had a previous pregnancy or she's had a previous transfusion in her history. All right, so that's the point of that question. It just wants you to understand this is an IgG antibody. It only built upon exposure. So she has been exposed sometime in her past through transfusion or pregnancy. All right, and then you're asked about some selection of positive and negative controls for phenotyping. So remember, anytime you phenotype a patient or you phenotype donor units, we will always run controls. When you select your positive cell for phenotyping, it must be heterozygous positive. And the reason for that is we want to ensure that the antisera can detect the weakest expression of that antigen, right? So if our patient is, or donor is heterozygously positive, we want to make sure our antisera can detect the weak expression of that antigen. All right, we want to make sure we get a true antigen expression of our donor or our patient, whichever we might be testing. All right, so if you're using this panel here to select some positive cells from, and we are testing for big E antigen, we could choose for our positive cell, we could choose cell number 3, all right, is positive for big E and little e, and then cell number 6 is positive for big E and little e. Keep in mind though, your antigen expression, your big E and little e, they're not right next to each other in this panel. All right, so notice here is big E, and then you have little c and then little e. So make sure that you're looking at the right antigen. Okay, does everybody see that? So big E and then little c and little e. Okay, so make sure you're looking at the right antigen. So cells number 3 and 6 would be appropriate positive controls for antigen typing. For your negative controls, any of the E negative cells would work. So 1, 2, 5, 7, 8, 9, 10, 11, right? Any of those would work as negative controls. All right, notice at the bottom of this chart, this panel, you're given your phenotype of your patient. One of your questions asks, what is the potential genotype, the Rh genotype of your patient? So given that our patient is big D negative, all right, so this patient's Rh negative, he does not have the big D antigen, all right, so when you're writing out his Rh genotype, he is going to be little d on both alleles, okay? Notice that he is big C negative, so neither one of those alleles have the big C expression. So he is little c positive, so he has to have little c being expressed on both alleles as well. Same scenario for your big E. This patient is big E negative, so he is not having the big E antigen expressed at all. He only has little e being expressed. So the only Rh option genotype for him is little d, little c, little e / little d, little c, little e. Okay, that's because he is Rh negative, big C negative, big E negative, right? So he only has, of the Rh antigens, he only has little c and little e being exposed on his cells, or being expressed on his cells, sorry. So given that we have noted that he is big C negative, one of your questions asks, could this patient build anti-big C? And the answer to that is yes, because he is big C negative. So remember Landsteiner's rule, what you lack the antigen to, you can build the corresponding antigen to. All right, so if this patient were to receive big C positive red cells, or for females, if she had a big C positive fetus, meaning that the dad was big C positive, then she could build anti-big C, okay? And notice also that she is big E negative, so her having the anti-E is a possibility. It makes sense. Okay, so a few other questions. You have a phenotype question. What percentage of the general population shares the same D and little c phenotype? Remember, 85% of the population is D positive. Our patient is D negative. So 15% of the population would have the same D phenotype as this patient. And she is little c negative. And if you look at your chart, 80% of the population is little c positive. So you take 0.15 times 0.8, and you should get 12%. And then that last question, and it's really a frequency question. What would you rather deal with? If you're alone in a blood bank lab at midnight, would you rather have a bleeding patient in the ER that has an antibody to big E or little e? I hope all of you guys agree with me in that we would rather have big E, right? Because 98% of the population has the little e antigen. So it's going to be very difficult to find little e negative blood versus 30% of the population has the big E. So 70, you have more chances of finding big E negative blood than little e negative blood. So this exercise kind of puts everything together. Looking at the reactions of your panels, doing the crossing off procedure, knowing some additional blood bank techniques such as neutralization, enzyme treatments, and how they are used in blood bank, recognizing the characteristics of your antibodies and looking at your reactions in your patient plasma that clue you in on what type of antibody you're dealing with, and as well as interpreting antigen frequencies to determine how many units you need to cross-match, and then phenotyping, rather a patient or a donor, selecting your positive and negative cells. So if you guys have any questions about those activities, please let me know, and I will see you guys tomorrow for exam 5 review. That's our last lecture before the final exam. So let me know if you have any questions, and you guys have a good day. I will see y'all tomorrow.